All right, so we're going to continue the day 54 lesson, and we'll go ahead and continue to draw Lewis dot structures and compute the formal charge to see what the most stable configuration is, or the most natural configuration is. So we have NCS. We're going to go ahead and draw that molecule as a linear molecule, and we'll just assume that C is in the middle right now. And then we're going to compute the number of valence electrons. So we have 1N, for carbon rather, we have 1C. All right, and then we have an additional electron. And that's going to give us a total of 16. Again, the additional electron, because it's an anion right there. All right, so we're going to go ahead and follow the rules. And the rules say we configured them in the way we think best. The least electronegative is in the middle of carbon, nitrogen, and sulfur. But when we look at the periodic table of electronegativities, we see that carbon and sulfur both have a 2.5. So we'll start with this one and see which one is the best. So we go ahead and draw single bonds. Again, why is this a single bond? Because these are covalent bonds. They're sharing electrons. So one of these electrons, let's say it's this one, is contributed by the nitrogen. The other one is contributed by the carbon. Remember, they're two strong guys. Neither one can pull the electron away from the other, so they share them. So that's a single bond right there. Those two electrons, one electron from each of the elements. Same thing on the carbon-sulfur side. So we've used 4 out of the 16. Now we create octets, and we go ahead and we do that by placing electrons all the way around the outside. Okay, so the next rule, we're on rule 3, and that's placing remaining electrons to create octets. And you do that on the outside atoms first. Okay, so nitrogen and sulfur have an octet. We have used 16 electrons. However, carbon does not have an octet. So how do we fill the octet? We take 2 from the outside of sulfur, and we take 2 from the outside of nitrogen, and we create double bonds. Okay, and we'll see that everyone now has an octet. Nitrogen has 8, carbon has 8, sulfur has 8. Now we're ready to go ahead and figure out our formal charge for this. And so the formula, again, is number of valence electrons minus number of non-bonding electrons minus 1/2 number of bonding electrons, those that are in between two elements. Okay, and so we'll just follow those rules. All right, so here we go. Nitrogen is 5 minus 1, 2, 3, 4 minus 1/2 of 1, 2, 3, 4 is 2. 5 minus 4 minus 2 equals -1. Carbon, 6 minus 0, no non-bonding electrons in there, minus 1/2 of 8. Again, I'm sure carbon is not 6. Carbon is 4. Correct that. So 4 minus 1/2 of 8 is 4, is 0. And finally sulfur. And sulfur, that is 6 minus, it has 1, 2, 3, 4 on the outside, 4 electrons, minus 1/2. 1, 2, 3, 4, half of 4 bonding electrons. And that equals 0. So this is a pretty good configuration right here. It has to end up with a -1 total. You add these three numbers, you should get a -1 because it is a -1 charge to start with. So this one is certainly the correct one, but let's go ahead and do the other two as an exercise. Okay, we're going to put nitrogen in the middle. All these numbers still apply, and we're going to surround everybody. And you can see the same situation occurs with the nitrogen not having an octet, so we're going to erase this. So you'll see you're going to end up with the same configurations no matter which one is in the middle. Okay, it's just the arithmetic over here is going to be different. So we'll start with carbon. And that's 4 minus 1/2 of 4. 4 minus 1, 2, 3, 4 non-bonding minus half of 1, 2, 3, 4 bonding. And that's going to equal -2. Nitrogen next. And that's 5 minus 0. There aren't any non-bonding electrons, minus half of 8. And that's 4. So that's going to give us a +1. And finally sulfur. And sulfur is going to be 6 minus 4 minus 1/2 of 1, 2, 3, 4 bonding electrons. That's 2. So 6 minus 4 is 4, minus 2 is 0. All right, so what you see here is when you add these three up, you still get a -1. You have to. If you haven't, then you made a math error somewhere, arithmetic error, okay? But you see these numbers are not as close to 0 if you take them as a group here as these numbers are. So let's go ahead and do sulfur in the middle. And we know we're going to end up with the same configuration. Okay, so let's go ahead and do this one, nitrogen. Minus 4 non-bonding, minus 1/2 of 4 bonding. It's -1. Sulfur's next. There aren't any non-bonding. And there's 8 bonding. And that's going to give us a +2. Rather a +2. Okay. And carbon. Carbon has 4 non-bonding, and it has 4 bonding. Okay, and there we go. And if we add these up, we get -1. So, but however, these are definitely a long way from 0. They're not even close to being 0. So this would be our favored configuration. Okay. Move on to carbon dioxide. Okay, so let's do CO2. Carbon is the least electronegative. It should go in the middle. Again, just draw something that looks symmetrical. You don't know what the geometry is of this at this point in your learning, so we're just going to assume it's linear. Okay, we're going to connect with single bonds. We have 16 in all, so we're going to put them all around the oxygen. We've used 16, but carbon doesn't have an octet, so we're going to do exactly the same thing we did in the situation up above. Take these outside electrons. Does it matter whether you took a couple of these? No, it doesn't, but it just looks more symmetrical if you take the ones on the outside. And there we go. Everybody has an octet, and you've used 16 electrons, so that's a possible Lewis dot structure. So let's go ahead and figure out what this is going to be. Carbon. Okay, so carbon's in the middle. And so that's going to be 4 minus 0. There are no non-bonding. Minus 1/2 of 8. And that's going to equal 0. For oxygen, now you have two oxygens, but they're both identical in how they're configured. So you only have to do the arithmetic once. All right, so that's going to be 6 minus, they each have 4 non-bonding, and they have half of that 4 bonding. So it's 6 minus 4 minus 2 is going to be 0. So 0, 0, that's definitely the configuration. But again, just to test it, let's put one of the oxygens as the central atom and see what happens. It just doesn't look right. It looks lopsided, but let's just see what happens. So we're going to go ahead. We know the configuration is going to end up the same, so we're going to go ahead and create our double bonds here. Okay, so let's do the math on this. Now, here's what's different about this, is you have two different oxygens. This oxygen's configuration is not the same as this oxygen's configuration. So let's go ahead and start off with carbon. So 4 valence minus 4 non-bonding minus 1/2 of 4 bonding electrons. So 4 minus 4 is 0, minus 2 is -2. So already you see we are not looking at something that's going to be that stable. Let's do oxygen, and I'm going to call it oxygen left, the one on the farthest on the left. So that's going to be 6 minus 4 non-bonding minus 1/2 of 4 bonding. So that's going to be 2 minus 2. That does give you 0. Now let's look at oxygen center. That's going to be 6 minus 0. There's no non-bonding electrons. Minus 1/2 of 8 bonding electrons. So half of 8 is 4. So 6 minus 4 equals 2. And you can see that these three numbers added up do give you 0. They need to, because carbon dioxide is not an ion. So that's that. But you can see that this is not as close to 0 as this. This is perfectly 0. This is not. This has got 2's in it and -2's. All right. So that's how you would do that, and that's why this is the proper configuration for carbon dioxide. Okay, let's do N2O. This was one that I believe on the sheet it said N2O minus, and you should correct that. So let's go ahead and do that one. Okay, so we have 2 nitrogens times 5 each equals 10, and 1 oxygen times 6 equals 6. It's going to give you 16. So let's go ahead. Now what goes in the middle, the N's or the O's? Well, nitrogen is less electronegative than oxygen. However, there's 2 of them, so that makes it a little bit confusing. So this is one where it's good to exercise this, to check the formal charge and see what the proper configuration is. So we've got really 2 possible configurations. Well, let's try this one. N, N, and O. All right, so we're going to do this. We have to take care of 16. We're going to do this. We've used 16, but we're in the same situation as the last 2. Trust me, this doesn't always happen this way. It just seems to be happening on these particular compounds. So we're going to create double bonds inside. All right, and there we go. And so we got everything set up. So now let's check the formal charge on this. So again, we have a nitrogen left and a nitrogen center because they're not exactly the same configuration electrons around them. So we're going to do nitrogen left, and nitrogen has 5 valence electrons. There's 4 of them here that are non-bonding, and half of the other 4. So it's 5 minus 4 minus 2 equals -1. Now let's do the nitrogen center. And that's 5 minus 0 non-bonding minus 1/2 of 8. And that's going to equal 1. And then we have the oxygen. There's only one, so we just call it oxygen. That's going to be 6 minus 4 non-bonding minus 1/2 of the bonding. And that's going to give us 0. And these three numbers add up to 0, and that's what you want, -1 plus 1 plus 0. So, and that's what you want. That's what you need to have. Okay, let's see if we can get something that's better than this with the other configuration. There's only one other configuration. That's going to be NON. Okay, again, same configuration of electrons. So let's go, and since the ends are identical, they're just symmetrical to each other. They both have, let me get rid of this actually. They both have 4 non-bonding electrons and 4 bonding, each of them do. We only have to compute N one time. So let's do that. Okay, so 5 minus 4 is 1, minus 2 is -1. And then the O is going to be 6 minus 0 minus 1/2 of 8 equals 2. That's 1/2 of 8 equals 2. All right, and then, okay, well, let's do the other one just because we need to make sure the numbers add up properly. So I'm just literally copying this one because they are the same. 5 minus 4 minus 1/2 of 4 equals -1. The reason I did that is you need to make sure the three numbers add up to 0, and they do. Okay, but this one appears to be the closest to 0. If you're not sure, what you're supposed to say is which. Well, that settles that. Okay, and so now there's a third configuration actually. We're looking at all the possibilities. I'm going to write it up here, and it's this one. You've got a nitrogen on the outside, a nitrogen in the center, and an oxygen on the outside. And then what you have is you have a triple bond between the nitrogens and a single bond with the oxygen. Okay, so there's 8 electrons around oxygen, and there's 8 around this nitrogen and around this nitrogen. So that's another possible configuration. And the two nitrogens are different. So we're going to do N left. And that's going to give us 5 minus, it has 2 non-bonding electrons, minus 1/2 of the bonding electrons, 1/2 of 6. So 5 minus 2 is 3, and 1/2 of 6 is 3, so that comes out to be 0. We have the N in the middle, in the center, and that's going to be 5. There's no non-bonding electrons, minus 1/2 of 4, and that's going to give us a 1. And then finally we have the oxygen. There's only one of those, the oxygen, to do that, and there's going to be 6 minus 6 minus 1/2 of the 2, so minus those 6 minus 1/2 of these 2. 6 minus 6 minus 1/2 of 2 is -1. Okay, so now we have an alternate configuration. We have a 0, 1, 1 here and a 0, 1, 1 here, so it's a tie. So between these two, which is the most stable? So there's a rule we haven't had to use yet, Okay, so we have a tie here between which we should choose. They both are identical. So let me add a seventh rule, which I should have added on your notes. I'm going to have you add it right here. So number 7, if there's a tie, meaning they're identical, I'll just write it that way. If the formal charges on two different configurations are the same, and that's what we have here, choose the one that has the most negative number on the most electronegative element. Okay, so let me read that again. If the formal charge on two or more configurations are the same, choose the one that, sorry about that, choose the one that has the negative number on the most electronegative element. All right, so we look here, and the most negative number in this one is on the nitrogen. The most negative number on this configuration is on the oxygen. Oxygen is more electronegative than nitrogen, therefore we're going to choose this configuration. So it's actually the configuration with the triple bond that's going to be the most stable, and that is the configuration for N2O. Okay, 2 more to go. I'm going to do these fairly quickly here, so hopefully this is all becoming kind of second nature to you. So it's 1 times 5 So you do have an anion, negative charge, so you add the extra electron in, and you get 24. All right. So NO3, what would that look like? Well, we tend to want to think that it's going to look like a nitrogen with oxygens on each side of the nitrogen. That's a possibility. We don't know for sure, but we're going to maybe guess that that's the case. Okay, so let's go ahead, and actually I prefer to write this just so everything's kind of linear, vertical, horizontal, rather than triangles. We'll get into that geometry next week. So let's go ahead and write this. All right, so there we go. So now we're going to place single bonds between these. All right, and then we're going to place octets around the outside atoms. Okay, and let's see what we have. We have 8, 8, and 8. That's 24. But what that means is that nitrogen does not have an octet. Can we get an octet there somehow? The answer is yeah. What you would have to do is take one of the pairs from one of the oxygens, and you can pick which one you want to pick. And we're going to make a double bond here. So now this oxygen still has 8. Now the nitrogen has 8. This oxygen and this oxygen did not change, so they still have 8. So we've used 24, and everyone has an octet. So that's going to go ahead, and that's going to be our configuration to test out. Now you'll notice you have some resonance structures here. The double bond could have been on this oxygen or on this oxygen, but that's just arbitrary which one you choose. That wouldn't really change. It wouldn't at all change the formal charges at all. You'd end up with the same exact formal charges. So we don't really consider those to be different. So we really just have one structure right here. And we're going to do that. So let's go ahead. So we have two single bond oxygens. So I'm going to call those oxygen singles. It's just whatever you need to do to identify them. Those are the single bonded oxygens. Okay, so we're going to start with those. So they each have a valence of 6. They're both identical. They each have 6 non-bonding electrons, and half of the bonding, they each have 2 bonding electrons. We're talking about this oxygen and this oxygen right here. And what that gives you is 6 minus 6 minus 1 is negative 1 right there. Now we're going to do the oxygen double bond. And that's going to be 6 minus, it has 1, 2, 3, 4 non-bonding, minus half of 1, 2, 3, 4 bonding. So 6 minus 4 minus 2 is 0. And finally we have the nitrogen in the middle. Alright, and that's going to be 5 minus 0, it has no non-bonding, minus half of 4 bonding, or rather 8 bonding electrons. That's going to give you positive 1. Okay, now before you stop, remember that you have 2 of these O singles. And if you just want to make a note of that, or you can just write it a second time, but it's exactly the same as this one. They both have the same configuration. And we need that because we need to add up these final charges and have them come out to be negative 1 because it is an anion. Okay. So that's going to be half of 2. That's going to equal negative 1. So negative 1 plus 0 plus 1 plus negative 1 does give you a total of negative 1, and that's what we have because of the anion over there. All right, so anyway, that's the formal charge for that. If we moved this bond around, this double bond, as I said, it wouldn't change the formal charge at all. It just changes the position of where the double bond is. But what if we move the nitrogen on the outside? Let's see what happens with that. All right, so we're going to do this. Put an O in the middle. Doesn't make any sense really to do that, but let's do it anyway. And so we can still form octets exactly the same way. All right, so let's see what we're looking at now. Okay, so now let's do the 2 single bonded oxygens there, and they are going to be exactly the same as what they were up here. So let's just write that O single, and that's going to be 6 minus 1 half of 2 equals negative 1. Let's just go ahead and write it a second time because we have 2 of them. Again, the reason you're doing that is because when you add up these final charges here, they have to add up to negative 1. So you need to have that negative 1 there twice. Okay. Next is the other oxygen. That's the oxygen double. And that's going to be 6 minus, it has 1, 2, 3, 4, minus half of the bonding, 1, 2, 3, 4. And that's going to equal 0. All right, and then finally the nitrogen. Nitrogen's in a different position now. Okay, and we're going to put that there, and that's going to be 5 minus 4 minus 1 half of 4. And that equals 1 minus 2 is negative 1. Okay. Okay, and I made a mistake here, so I hope you caught it. Let's go back to the oxygen double. It has no non-bonding electrons, so that why I put a 4 there is a mystery that only God knows. Okay, there's that, and then it's half of 8. It has 8 bonding. All of its electrons are bonding, so that should be an 8. What I saw, I'll tell you what I saw, is, and I stopped the video for a moment, I saw that this didn't add up to -1. It has to. So that's one of the reasons you do this, is to check your work. Okay, so now I have 6 minus 0 minus half of 8 is 4. So 6 minus 4 is positive 2. So now if I add these numbers up, -1, -1, -1 plus 2, I do get -1, and that's what I have to get because it is an anion right there. All right, so which looks the most stable? Well, definitely this one, okay? It's got numbers that are closer to 0. This has got numbers all over the place, including a positive 2. So we're going to choose this one up here. That's our most stable structure. All right, I hope this is becoming kind of natural to you by now. We've got one more to go. Selenium dioxide. So let's go ahead and do that. And I'm going to be totally quiet and just do it. Except I will say this. Remember that selenium, even though it's down in the 4th row and there's all those transition metals in the middle of the periodic table, they do not count as valence electrons. Only the first 2 columns and the last 6 columns. And we're going to get into that this coming week, okay? So selenium has 6. If you look at the elements above it, sulfur and oxygen, they have 6. So it's the same as those. And I'm only going to do one configuration for this one. Okay, so we've used 16, we need 18, and selenium only has 4, so we have to add 2 more to get up to 18.